In this lecture, we'll continue looking at residual management, but in this case, we'll focus on wastewater sludges. So there are a number of types of residuals that are produced in a wastewater treatment plant. These include the material that's removed from bar screens and the material from grit chamber. These are not true sludges because they're not fluid. They can be drained easily, and they tend to be relatively stable and then can be disposed of directly in a municipal landfill. In some cases, the grit is washed, and that wash water then is directed back to the headworks of the treatment plant. We also have primary sludge. So just to reiterate, we drew this last week, but let's do it again. Okay, so water comes in from the sewers to the wastewater treatment plant. The first process is typically
a bar screen.
Okay, the bar screen. After the bar screen, it goes to
Grit chamber.
The grit chamber.
Primary clarifier.
From the primary clarifier. Someone else.
Oh.
Anyone else? Okay, we've got aeration, good. From aeration into, where does the water flow after the aeration tank?
Can I say it?
So the secondary sedimentation or clarifier. And if you may recall, the return activated sludge is pumped back into the aeration tanks because these are the microorganisms. So secondary, and then we have waste activated sludge, and then the effluent goes typically to disinfection and then to discharge. So that primary sludge that is produced from the primary clarifier typically contains about 2 to 80% solids, and it's about 60 to 80% organic. So challenges with treating this are that it becomes anaerobic quite readily, which means then it's going to produce hydrogen sulfide gas, methane gas, and CO2. What are the dangers there? Said it was malodorous, but what are the dangers? Hydrogen sulfide and methane are explosive gases. So one of the challenges is really during storage and making sure that your operator, all of the plant operators are safe from exposure, both they're toxic, but also from explosions. And then there's the secondary sludge, that's our waste activated sludge. And that consists of these wasted microorganisms and inert material. Like the primary sludge, it also contains about 60 to 85% organic matter, but the percent solids is actually quite a bit less than that of the primary sludge. And it's also a less dense sludge because of the microorganisms. Your microorganisms have a specific gravity, slightly less than 1. We mentioned this when we talked about fixed and volatile solids in calculating specific gravity of the sludge. And the other challenge with this is that metals, toxic organics, viruses can all attach to this organic matter. So one of the challenges of disposal is making sure that the disposal of this material is done in a safe manner. And in fact, one of the concerns is with biosolids. You'll see that with the PFAS chemicals that we talked about. In Lapeer, this was a major issue in that there was a plating facility that was discharging PFAS. It was not regulated at the time. that PFAS chemicals then were discharged to the sewer, to the wastewater treatment. They enter the wastewater treatment plant, and they ended up in the biosolids. And those biosolids were land applied. So then there's the concern about incorporation of the PFAS chemicals into the plant material, the crops, and then what impact that has. So what you will see in the next few years is a lot more concern about these chemicals in the biosolids and how do we safely dispose of these biosolids. If we land apply, how do these chemicals then migrate through the environment? And then if we have tertiary sludges or tertiary, and if we have tertiary treatment, then we have those potential solids. So for instance, in the East Lansing plant, we have aeration, and they add ferric chloride at the end of the aeration basin. That ferric chloride is added to precipitate phosphate as ferric phosphate in order to meet their regulatory limits. But then the sludge from the secondary clarifier also contains ferric phosphate. And that can make the treatment of that sludge more difficult. Denitrification sludges, so that's sludges where we're converting nitrate to ammonia gas, tend to be similar to the waste activated sludge. Now at the East Lansing plant, the water goes from the aeration tank into the secondary clarifier, and that effluent then goes to tertiary filters before disinfection. Do we have any additional residuals from this process?
That'd be the concentrate from the tertiary filters.
So the tertiary, they would be if they were membrane filters, and I should have explained, these are actually sand filters, so they're gravity, but you're onto it.
Backwash from sand filters.
The backwash. And where does that water?
Back to the headworks.
Exactly. Can't discharge it to another sewer, to the sewer. Well, if we do, it basically just goes back to the headworks anyway. So what you'll see, same is true for your grit wash water. That goes back to the headworks. Backwash water goes back to the headworks. Any supernatant from any dewatering processes that we'll talk about goes back to the headworks. You can't discharge that material. So when we're looking at sludge management, there are really 5 aspects of this. One is to minimize sludge generation. If we can minimize sludge generation, we minimize the treatment processes, which saves in terms of energy production, consumption, and saves in terms of cost. So the first aspect is minimizing sludge generation. If we can chemically recover precipitates and actually reuse them, that would be optimal. It's much more difficult to do in a municipal wastewater treatment plant. It's more feasible in an industrial setting. We want to reduce the volume of the sludges, so we're going to treat it. And we mentioned that we need to reduce the volume. Why?
You can make the processes later on smaller sizes.
Okay, so we want smaller sized processes. We have to do any subsequent treatment. And why else?
The sludge is mostly water, so
we want to reduce transportation and disposal cost. We want to ultimately dispose of it in an environmentally environmentally friendly manner. So we want to avoid the issues that I mentioned, for instance, with the PFAS chemicals. And most importantly, we want to protect human health and the environment. And I've included here the ASCE Code of Ethics. They have been recently revised and repackaged, but what used to be called Canon 1 is now 1A, and that civil, and this is ASCE, but applies to environmental engineers as well as civil engineers, and it's really across the board. For engineers, first and foremost, their responsibility is to protect the health, safety, and welfare of the public. So as you mentioned, with many of these sludges, we're dealing with chemicals or the potential production of chemicals that are explosive. So we also need to protect the workers and the community that's surrounding the plant. So when we look at sludge treatment, typically we can divide it up into thickening, conditioning, dewatering, thickening, and disposal. So thickening is the initial process. So for instance, at the dye treatment plant, this is the Lansing, the sludges from their lime, the sludges from the lime soda ash processing, so from that sedimentation basin, first go through gravity thickening, and we'll look at some photos of this. They actually don't need to condition, and then it goes through a plate filter press. So we'll look at how some of these processes are used, but thickening, basically we're doing an initial attempt at removing some of that water. It helps equalize the flow for subsequent devices. It also allows for the subsequent devices to be sized much smaller. Conditioning, where they're typically adding chemicals, it can also be adding heat. And what we're looking at is we're processing that sludge so that the dewatering process is more effective. And then dewatering, we're minimizing the volume in order to prepare the sludge for final disposal. Okay, so from there, we go in and we can start looking at some of these processes. So if we're looking at flotation, what we're trying to do with flotation is, remember, we have the sludge, and often that sludge or those solid particles are less dense than water. If they're less dense than water, it's very difficult for those particles to settle. We need a very long period of time. So what we do is we inject bubbles of air. Those bubbles rise to the surface, attach to your particles. The particles rise to the surface and then float at the top. So for secondary sludge, flotation is often much more effective than gravity thickening. The East Lansing plant uses flotation to thicken their sludge before disposal. It's just a short video.
The air introduced by the Flowmar air power system forces the flocks to the surface, where they are skimmed off. The flotation process is used in the EnviroChemi systems Flowmar and Lugan, and is especially suitable for the kinds of organic wastewater that is produced in the food and meat industries.
But you can see in the image how these particles float to the surface. This is also used in the paper and pulp industry, and as I mentioned, used in many cases in wastewater treatment, municipal wastewater treatment. So this is just the flotation process. Again, it's very similar. It's essentially the opposite of a gravity settling process. Here if chemicals are added, they're added in this initial reaction tank. The dissolved air is added here, and then the particles flow to the surface and they're skimmed off to a sludge hopper that you see here. This is a gravity thickener. And this is the image is actually this is the gravity thickener at the Lansing Dye water processing facility or water treatment plant. So that sludge from the sedimentation basins are then pumped into this sedimentation basin. It operates as exactly as a sedimentation basin that we've discussed previously. And here what they're doing is they're dewatering or thickening that sludge for the subsequent process. So where does the supernatant go? So in a plant like this, where will the supernatant go?
Also just going to be back to the headworks.
Back to the headworks. It has a high pH. Remember, we want to raise the pH of our water in order to precipitate the calcium and magnesium. So we can actually use this water to help raise the pH. So it's just pumped back to the headworks of the plant. If we can minimize discharge, it saves us money, it saves us processing. If we can reuse it, and so it's actually reused in the plant to help operation. Now, if we're looking at thickening, we can thicken or if we look at conditioning, So when we're looking at conditioning, we can add chemicals. So these are typically coagulants. So it could be lime, ferric chloride, alum. It can also be polymers. And these are added just prior to dewatering stage. Or we can heat treat. Now, the heat treatment is done at high temperatures and high pressures. And because of that high temperature and high pressure, the water that's bound to these particles, to this flock, is easily released, and the sludge is then dewatered. The problems, it's a complex process. That bound water that's released is highly concentrated, which then has to be directed to the headworks of the plant. Depending on the operation of this, that can lead to shocking, which means you're providing high dosage of this concentrated stream, and that can affect your other processes. It also has high capital costs, high operating costs, because you're dealing with high temperatures and high pressures. But the advantage is that you can produce sludges with about 50% solids content. So you can produce a high concentration of dry matter in the sludge, but it costs in order to do that. Now we can also use non-mechanical means, basically lagoons. The photo that's shown here is an aerial photo of the East Lansing Meridian Township water treatment facility. And the lime soda ash sludge is then pumped out into these ponds. The different colors is because of the way light refracts or is refracted off of the water in these ponds. So the one that's white has the highest solids content. So basically these operated as a fill, settle, decant. So when they're filled and you've achieved the desired solids content, the lagoons are then excavated. And in the case of the East Lansing plant, that lime soda ash sludge is then land applied to fields as a soil amendment. It can help raise the pH of soils. So it's used in that way. The lower photograph is another photograph of the lime soda ash ponds in the East Lansing plant. And if anybody has any questions as we're kind of walking through these, feel free to ask. We can also use sand drying beds. In this case, there's sand and the water actually permeates through that sand and then is collected. These are, again, they're simple, they're low maintenance, they're affected by climate, as is the lagoon system. And they require a significant amount of land area. We can use centrifugation. So we centrifuge the sludge. Typically, polymers are added to condition the sludge. The challenge with these is they're very susceptible to changes in the sludge composition and characteristics, and we need pilot testing to operate these. A question about chemicals leaching into the aquifer from the sludge lagoon, yes. The East Lansing ones are lined, so you want to make sure that you have a lined lagoon so that you can minimize infiltration into the aquifer. The supernatant from the sludge lagoons up until very recently were then piped back into the plant, to the headworks. But that meant that the East Lansing plant was a groundwater under the influence of surface water. They now have processing for that water, and that is disposed of to the sewer. So they've changed their operation because of the additional requirements that are needed when they are a groundwater under the influence of surface water. We can also use vacuum to pull out the water. Basically what these are, sludge is then goes through, it's collected on a cloth. Vacuum is pulled through that cloth and to pull water through it, and then produces this sludge cake. These are operated with a differential pressure of about 70 kilopascals. And then we have the belt filter press. So these operate by, got an image on showing this, but the sludge cake bends between two filter belts around a roller, and that roller introduces shear and compressive forces and allows the water to move to the surface out of the cake and can be used in this way. So you can see it here. So we've got, initially, we're relying on gravity. Yeah, I'm not sure exactly why. I assume there's an issue. There's a tremendous delay in the video. I'll re-record this later. I apologize for the audio issues. And we haven't had this kind of a delay that as I watch from my tablet to my laptop, I can actually see that a visual delay, and there was a significant delay in the video. So I apologize for that. Not sure what I can do. The joys of being remote. So I apologize. So basically with these, what you see is you've got this gravity drainage, then you've got the compression dewatering. So you've got a lower pressure. And then as this sludge moves across these rollers, then that helps to discharge the water. Again, the water is transported to the headworks of the plant. And then typically these are installed on a second story. And that's so that you can place a hopper below it. And you'll see this in one of the next videos. So you've got a hopper below it, and the sludge actually just falls directly into the hopper. So then it can be transported from the facility. These are relatively low energy compared to many of the other dewatering devices. again, polymers are often used. So this is a belt filter press. We'll see if this. So you can see the sludge as it flows. And then there's a series of rollers. So you see the sludge coming in, goes across a series of rollers. And then you can see that thickened sludge. So it comes in, it flowed initially, and it's a much thicker sludge after processing. Plate filter presses require prior thickening. So as I mentioned, appears it has not advanced yet. Okay, so now we have it. So as I mentioned with the East Lansing plant, the Lansing plant, they thicken the sludge with gravity thickening, and then the sludge is pumped into this plate filter press. So these work by the sludge being pumped into this pressure filter. It passes through a series of feed holes into these filter plates. The pressure is placed on it, forming a filter cake. And that filter cake, then these open and the filter cake falls, in the case of the Lansing plant, into a hopper. And this picture is actually from the Lansing plant. Typically, it takes about 20 to 30 minutes of pumping of sludge into the filter press. When it's full, then the pressure is applied at the maximum level, which is typically between about 700 to about 1700 kilopascals. And that pressure is maintained for about 1 to 4 hours before these plates are opened. And what you're seeing is the process here of the plates actually opening. And then in the next video, you'll see the sludge actually falling from the plate filter press. These typically require routine washing. They also require an operator to be present during the opening. They have to make sure that all of that sludge that has the cake that's formed on this plate falls into the hopper. Any cake that's left on the hopper can result in areas where you don't get sufficient closure of these plates. And then when you apply the pressure, that sludge basically shoots to the ceiling. And we got to see the plant. You actually can see sludge on the ceiling where this actually occurred. Again, this is at the dye plant. You see it opening. It really is this loud, and you can see I have a really short video, but you can see that sludge falling, and it's falling into a hopper and then can be trucked away. You see it fall there. This is another video. Here it's a little bit longer. Again, you see the same. So it's not as apparent as the dye plant, but you can see a little bit the sludge falling at the bottom. I added this table from the textbook. just as an attempt to kind of give you a sense of the differences in the sludge contents, perhaps also beneficial if you need it for mini design 3. We've been talking about wastewater sludges. So the last part is to look at volume reduction. And we had talked about that as important in this case where we're looking at digestion. There typically is no subsequent process. The sludge from the digester is then trucked off to one of multiple locations, and we'll talk about that. So aerobic digestion is basically an extension of activated sludge. It's accomplished by aerating the sludge, just like one does in an aeration basin. The difference is that we're taking that waste activated sludge, and that goes into the aerobic digester. The supernatant from that goes back to the headworks of the plant. That supernatant is highly concentrated. It's got a high concentration of BOD, total caldol nitrogen, and total phosphorus. And your treated sludge typically has about 3% solids. The goal is to meet the regulations and 40 CFR. CFR is the Code of Federal Regulations, Part 503, are the standards for use or disposal of sludge. So these are the requirements that must be met in order to either dispose of sludge to perhaps a landfill or to use it as a land amendment or a soil amendment to apply it on land. So the basic premise of this regulations are to reduce pathogens, reduce vector attractions. We want to make sure that we're not transmitting disease through various different vectors, for instance, insects, rodents, etc. We want to reduce the volatile settled solids, and that requires what's typically referred to as degree days. So that is the detention time times the temperature in degrees C. The alternative in terms of digestion is an anaerobic digester. So an anaerobic digester operates in the absence of oxygen. The advantage of aerobic, and we'll talk about safety issues with anaerobic, but the major advantages are it's safer, it has a lower capital cost, it has a relative ease of operation. So those are the advantages. The disadvantages are in turn compared to anaerobic digestion. It has a higher energy cost, and it's also very much temperature sensitive. And that's basically same premise. You're converting BOD to COD, to nitrogen to nitrate, phosphate forms to organic phosphate to inorganic. When we're looking at aerobic digestion, notice here, okay, we're adding oxygen. So what are we doing here? We're converting that biomass to CO2 and producing ammonium ions. So we take that nitrogen from the biomass and converted it to ammonium ion. This tends to result in an increase in pH. We use oxygen, we produce CO2. Nitrification, we're looking at taking this the ammonia that we produce. Okay, looks like we're back. Sorry. Nope, it was my Wi-Fi here. I apologize. Okay, so the ammonia is converted to nitrate by nitrification. Typically, this is going to result in a decrease in pH. Notice we're producing H+. We need more oxygen to do that. 3 is just the sum of basically 1 and 2. So we're looking at digestion with nitrification. I'm going to skip 4 because it's basically the same thing. 4 is denitrification. And here what we're doing is we're taking this nitrate that we produced previously, and we want to convert this to nitrogen gas. Ideally, we don't want ammonia. We want a complete conversion to nitrogen gas. So you can see we need a significant amount of oxygen. We convert the carbon to CO2, and we're converting the nitrogen to nitrogen gas. So essentially that's what's happening in an anaerobic digester. So as I mentioned, it's very much temperature sensitive. Ideal temperatures are between 20 and 30 degrees. We want the temperature above 5.5. Less than that, that inhibits the microorganisms. It's affected by, refer to the stability of the sludge. So basically how effective these reactions are, and the biological diversity, what organisms we have present. And as I mentioned, the regulatory requirements are pathogen reduction and vector reduction. So we want to make sure that we're not transmitting disease through various vectors such as insects and rodents. This is just a photo of an anaerobic digested dewatered sludge. You can see it here. It's this very black. It looks kind of like topsoil. And as mentioned, these photos are actually from the author, from Dr. Mackenzie Davis, and he noted that odors do not appear to be an issue. It's a open storage. You can see there's homes very close by. So you get a waste that really does not have a significant odor. So now that's aerobic digestion. Anaerobic digestion is done in the absence of oxygen. So it's a series of reactions. The first being a hydrolysis reaction where we're taking the fats, the proteins, the polysaccharides that are left in this waste that didn't get oxidized in the in the aeration basins. So this is in the sludge. Those get converted to triglycerides, fatty acids, sugars, and amino acids. The next step is acid fermentation. Now, these compounds are then further oxidized to produce volatile fatty acids, many of which are extremely malodorous, alcohols, and new bacteria cells. In both step 1 and 2, we're not achieving much reduction of the BOD or the CO2. We're not stabilizing. When we talk about stabilizing, we're talking about forming compounds that don't consume oxygen in the environment. Acidogenesis or acetogenesis results in either the formation of acetic acid or hydrogen and CO2. So it's one or the other. You'll see in the next slide. And then finally, methane fermentation results in the formation of methane gas and CO2. So we think anaerobic digestion, we're looking at, in terms of stabilizing the carbon, we're stabilizing it to CO2. We're also producing methane, and that methane can be used as a fuel. This is basically the same pictorial image of what I just said, and you can see we produce these volatile fatty acids, and then we can either produce acetic acid or we produce hydrogen and CO2. Either way, we produce methane and CO2 as the final products. These systems are operated at higher temperatures, so you can see the temperature is higher than for aerobic systems. pH needs to be between 6.8 and 7.2. If it's less than 6.8, it results in what is referred to as souring. Souring of the digester means that the methane formation is inhibited. The contents of the digester become acidic, and that is a significant problem. So one wants to make sure that there's sufficient alkalinity so that when acids are being produced, that pH doesn't decrease below 6.8. We also need to make sure that it's free of toxic compounds. And this is extremely important. That methane that's produced, as I mentioned, can be used as fuel. Your digester has to be heated. So for instance, at the plant that my dad worked at for many years, they had anaerobic digesters. They heated all of the digesters with the methane that was produced. They ran the blowers for the aeration tanks with that methane. And they actually sold off excess methane to the power company, Public Service Gas and Electric. That worked wonderfully until the plant superintendent decided that they could make some significant money by allowing industrial waste to be discharged to the sewer. Well, this is quite a few years ago. There were few pre-treatment requirements for this industrial waste. So it went from essentially almost entirely a municipal plant to a municipal plant with industrial discharge. That resulted in significant increases in various toxic chemicals. Their methane production decreased significantly and actually resulted in them having to supplement the energy needs in the plant with natural gas in order to, or probably diesel at that point in time, actually, in order to provide aeration and to heat the digesters. So it's extremely important that you make sure that the wastewater coming in is free of toxic compounds. Advantages: you're producing methane. It's a significant energy source. You're not adding oxygen, so you're saving on the need to aerate the system. And as with aerobic digesters, the supernatant goes to the headworks of the plant. You've got to keep, it's essentially a recycle loop. There's no place to discharge that supernatant other than either the environment, which would be of significant, call it a disaster, negative impact on the environment, or to recycle it back to the headworks. These are just some images of a single stage and a high rate digester. So you see a single stage digester. These require a large tank volume. They require a long detention times, typically 30 to 60 days if it's heated. They have low loading rates, and they have this thick scum layer. And actually, if you see that the active digestion layer is typically only about 1/3 of the tank volume. The rest are the supernatant and the scum layer, digested sludge storage, and gas storage. A high rate digester, on the other hand, is completely mixed, requires, again, a heat exchanger, and the digested biosolids are discharged from the bottom and your digester gas from the top. And again, we have a recycle back to the headworks of the plant. A two-stage digester is basically a combination of a standard and a high rate digester. So the first stage, fermentation occurs. It's mixed and it's heated. And the second stage, the solids are separated. And you can see, so you've got the solids separating, you've got your scum layers, you've got your scum removal, gas on the top, and an active digestion zone. These are just some photos, again, from the author, from Dr. Mackenzie Davis, and just showing you, typically these have a floating cover. The flexible, these are the flexible compressed gas lines, and they need to be flexible because your cover is floating depending on the amount of gas in the digester. Just some other photos. You can see here are the floating cover roller guides to allow it to move up and down. Lightning arresters, these are extremely important. Remember, we have methane. We don't want to ensure that there isn't the potential for a spark, in this case from lightning. And we've got a radar roof sensor, again, to make sure that the roof is level. This is the gas burner and boiler used to heat the anaerobic digester. It's very typical. There are significant safety issues. So what you see here are we have a gas monitor to ensure that we don't have any leaks of methane. Methane is an explosive gas. We have an explosion-proof light switch. We have explosion-proof light fixtures. So significant efforts have to be taken within the digester buildings to make sure that there aren't issues like this where there are explosions at the wastewater treatment plant. It's one very recently in the UK, last week, and 4 people died from an explosion. You can see the roof, how that has exploded. The one in 1976, I grew up on the East Coast. It's actually one that I remember, probably also because my dad worked not at this plant, but my dad worked at a wastewater treatment plant, and a child was killed when an explosion occurred at this treatment facility. So safety, as I mentioned, safety is paramount. We need to make sure that we do everything we possibly can to ensure that these systems are safe. Finally, we can also use incineration or wet oxidation as for volume reduction. As I mentioned, the city of East Lansing did incinerate waste. It was up through, I think it was the mid 90s or so that they were incinerating waste, their sludge. They stopped actually because of the state implementation plans for air quality in the area. It would have been too costly to have continued incinerating and to add all of the additional control technologies that would have been necessary on the incinerator. So they no longer incinerate, but one can incinerate biosolids. It's highly energy intensive because one has to completely evaporate the water from the sludge. And if your sludge is only 5 or 10% solids, that's a significant amount of water that one has to evaporate. So it requires fuel. The solid material is inert, so that ends up in the ash. If it's bottom ash, it ends up at the bottom of the incinerator. Fly ash, it has to be removed before it's released from the stack. And that requires that the exhaust gas be treated. Wet oxidation can also be used. This again requires energy. The solid material is also inert. So the disadvantage of these are you're not producing a waste that has any value. There's still a significant amount of, for instance, phosphorus in that waste that is a potential benefit. The waste is no longer beneficial if it's treated by incineration or wet oxidation. And then the ultimate disposal can be land spreading. This is regulated under the Resource Conservation and Recovery Act, known as RCRA, often used for lime soda ash sludges, and in some cases, coagulation sludges. Again, it must be designated as beneficial use, and it has to be permitted. It can also be used for applying on turf grass. Turf grass doesn't require significant nutrients, but the sludge can be used for water retention. It can be blended with topsoil, again, for water retention. It can be used as a road subgrade. It has to be quite inert. If it's degrading there, that's going to affect your subgrade. It can be co-disposed with sanitary sludges. So basically mixed, the water treatment sludges mixed with municipal sanitary sludges and then disposed of, and it can be landfilled. For wastewater sludges, they're designated as Class A or Class B, and that's based on the pathogen density. And they can be either landfilled. So for instance, the East Lansing plant has been landfilling their sludge. It's collected in a hopper, transported to the Granger facility, to a biological landfill, and the landfill, because it's a biological landfill, recovers the methane. So it does produce energy, but in the landfill. Or it can be used for dedicated land disposal. Again, one needs to be careful there and make sure that there's limited public access. There's restrictions as far as cultivation of crops, how that land can be used. And I mentioned a little bit the other day with Lapeer and the disposal of the sludge from their plant and challenges with PFAS. So hopefully this gives you a sense of treatment